Okay, everyone. So now let us look at some of the workings and some of the theory behind S25. So first, we'll begin with file generation. Okay, so since we all saw what exactly S25 is, it is not enough to emphasize how important file generation and file metrics is to the security of S25. Okay, so of course we can always begin with an arbitrary size, but there's always this uh, notion of being proper, because if I were to just generate an arbitrary file, then I can have these edge cases where the cascading function may not work properly, or uh, some other issues which can arise. Okay, so anyway, now let us look at just one of the let us look at English, and let's see what actually we can um, see. Okay, so now let's say I were to take a 10 key combination, which means there are like 10 messages being exchanged, and the cascade lasts for 9 of them. If I were to choose English, as we know, English is entropy. So E English is around 0.6 to 1.2, I think. This was done by Shannon. I mean, this live work was to calculate the entropy of English, and we found out to be 0.6 to 1.2 bits. Now, when we look at English, and then when we look at the characters in English, we get uh, an 8-bit. Uh, we have this 8-bit ASCII code. So what this tells me is that out of these 8 bits, only 1.2 bits are actually important, and the rest of them are kind of redundant. Of course, if we look at the first order of frequency generation, we get around 2.2. So this is taking into frequency. This also corresponds to the Zipf's law and actual experimental frequency. So this is going to be around 2.5ish, if I'm not mistaken. Yeah. Again, out of these 8 bits, there are only 2.5, which are actually important. Uh, so let's see what we can actually work with this. So let's say I have a 10 key combo, and uh, then there are 10 uh, length keys. So there are going to be 10 kind of um, letters, and then it's going to be around 10 times the message sent. So if we were to calculate the usual size of the file, so because what we need to make sure is, out of all these 10 keys, only after the 10th key is shared, the file has to have a unique state. So now if I plug in all of these numbers and calculate the size, I am going to be getting around 2 to the power um, 350 bits. This is extremely absurd, and we cannot actually come up with something very close to this. So what we can actually try doing is to drop down this size. Um, so if we make this 5, again when we do the entire combination, we get 2 to the power. So for 5, we get 2 to the power 175 bits. Again, this is extremely large. We don't have the technology to process these many amounts of bits. These are very, very large. So for something like English, we cannot really process this, but we can try for Mandarin or some other languages which have a little bit higher entropy. So those will have a much better kind of a thing. So again, if I were to use a 4-bit entropy language, so I'm going to be getting around 2 to the power 100, which is somewhat manageable number of bits. Again, we still don't have the technology, but we may in the very future have these kinds of things. So now let's actually calculate the files, the file sizes. Okay. So the probability of some message ki being in L, which is some file, is going to be 2 to the power minus 8 minus epsilon, where epsilon is the entropy of the language, times ki, where ki is the message. So let me just clear everything out. Let me just write it. So if I do have a summation, if ki is a summation, so then p of L comma ki, but it's a summation from I equal to 0 till some n. So this is going to be 2 to the power negative 8 minus epsilon times summation of ki. And now we see the without the LRM, if we were to do some kind of scaling, we look at this multiplication problem and then we think this is extremely huge and we cannot actually, the scales really, really fast, very quickly. That is the thing. Again, so there is a summation of n. N is the number of messages being sent back and forth. So again, if I want to scale it to a very high level, I just have to increase n. And then it scales exponentially. This is the probability that ki is present in L, where L is the length. Like L is the file. And then if we have to find out the actual expected length, all you have to do is just remove the negative sign. So S of L comma ki summation is going to be 2 to the power 8 minus epsilon times summation of ki. Okay, so there is a lot to unpack here. So the 8 comes from the 8-bit. So if I were to replace this with, let's say, some, what should I call it? Let's call it alpha. So alpha equal to number of bits used per character. Okay, so if we replace 8 with alpha, and then I can modify alpha to actually meet this time. I can scale it so that this number and this number are kind of are in some sort of a manageable range. So that is what I intend to do with LRM or the language redefinition module. But in the case of the vanilla kind of S25 without the LRM, it is going to be 8 and epsilon is going to be the driving factor. So if I choose a very high entropy language, I can get away with a smaller file size. And let's not forget that the file generation has to happen from random processes, and each bit is going to be represented by some random processes, whether it is let's say a computer running the numpy dot random integer, or maybe it's a nuclear radiation, whether an atom gives out a particular radiation or not, or even it can be something like collapse of a qubit in the orthogonal state. I mean the other plus or minus basis. Okay, so we will discuss this a little bit later on. So now, how do we generate a file which is this big? That's the question. And what exactly is the file size when I change the alpha? So if I change the alpha to something like 4 and epsilon to be 2, for 3 messages, I think I can get away with a million digit long file, which is somewhat around 30 MB. So let me just write that down. This is actually being used in my practical demo. So alpha is somewhat around 4 and epsilon is somewhat around 2. Sorry. Uh, yeah, epsilon is around 2. So the file size S is going to be equal to 1 million digits, or roughly around 2 million or something. Sorry, alpha is 2 here and epsilon is 1. Sorry, yeah, alpha is 4 and epsilon is 2. So it basically means that for every character that I use or every word that I use is going to be 4 bit long, and epsilon or the entropy of the language is going to be 2 bits. Again, this is a very crude calculation, and this is supposed to be the lowest scaling possible using S25. We can prove it later on, and there is a reason why I'm not choosing 2 and 1. That becomes apparent because it's the construction of S25. It gets in the way of me going much lesser than this. Of course, so this is going to be around 30 MB. Again, this is extremely manageable when we compare it to the 2 to the power 175 bits. And that is extremely large. So, okay. So now let us look at how what we can do to generate these kinds of files. So I came up with 3 options, which are somewhat feasible, or at least I believe is feasible. So first one is going to be using bit 0, and then using Hadamard gate and measure. So of course, if I apply Hadamard gate on qubit 0, I'm going to get 0 plus 1 over square root of 2, and then once I measure it in bases 0 and 1, I'm going to be getting either one of them in 50-50 probability, and then I can keep doing this for every single bit. Of course, I have to do a million or 2 million of these combinations. Okay, so there are other measures as well. So second one, what I can do is I can use numpy. Of course, this is a built-in function in Python. Dot random integer, and then so what I can do right now is I can do numpy dot d type, stands for data type. I can put this as int 8. So this is the closest that we can get to some classical optimization, because the random integer is going to take a 64 bit or 16 bit or whatever the integer is defined as. But if we can force it to be an integer of 8 bits, then it's going to be much faster. Of course, if I were to use a machine algorithm, I mean like machine or assembly like code, I can reduce it into d type equal to 2 bit integer or 1 bit integer, and that is going to be significantly faster. And but the problem with this is it's not actually random. This is because it uses something like clock speed, clock cycle, uh, local time, etc., to actually determine whether it is uh, whether what integer it actually is. But when we look at S25, it is somewhat like random enough that we can still use it and get away with, uh, you know, we can still use it and get away with not having to worry about someone actually reconstructing the code using this kind of exploits. Okay, so what we see here is we have to generate these files physically, and even if it is 30.4 MB or something, every bit has to be processed individually. So which means they're kind of efficient, but they're also not. So when I do take for a practical example, so when I was generating around 10-digit length file, so it took me around 10 minutes, and for 9 digit, it took me around few seconds to a minute. So again, this is just 10-digit file and 9-digit file length. But if we were to look at something like a little bit more advanced, or if I were to add some redundancy, again, these kinds of metrics are for the lowest scalable S25, which I can write the code right now. Okay, so now comes the third option, is to use large libraries. So of course I have many options in this. I can use movie series, library. So this can be physical library turned into ebooks or whatever. Or there is a huge workaround, and the size metrics are kind of in the favor. What we can do is we can look at game libraries. So this includes these multinational corporations such as Steam, Epic, Ubisoft, etc., etc. And these come usually around size of 100 gigabytes per game. Again, this is not a conventional uh, solution, but what happens during this game generation when they actually write the code for the game is that they have to render every single frame in a different engine. So each engine has its own kind of uh, the kind of like the inbuilt structure and how it actually works. So we have Unreal Engine 5, we have uh, you take ID Tech 7, so we have UE, we have ID Tech, and we have some more engines that we can that a developer has a choice to make these games out of. And of course, if they stretch for 100 gigabytes right now, they are going to be hyper unoptimized. So every frame has to be kind of generated from scratch, and then these things just get unoptimized, and then the file sizes can explode anytime. So again, so if we want to use these kinds of file, we have to run it through a 7-zip and check the compression ratio. So if the compression ratio is somewhat acceptable, something around 85, so like 85% or maybe even 70%, that should be fine. Um, so yeah, this is one of the ways that I can actually implement S25 without actually going to much depth right now. If I were to use these two methods, I need either a very powerful computer or a very powerful quantum computer, which is also very stable at these kinds of numbers. Okay, so that is all about size metrics. So let's move on to LRM. So yeah, before we go, the reason why I cannot use movies is because they can be compressed heavily using Huffman code, and of course libraries they can be compressed as well. Because when we are looking at something like natural languages, they have a very low compression ratio. I mean, yeah, so they can be easily compressed. Okay, so now let's look at LRM. Okay, so now let us look at what exactly this stands for. And we did look at some of its importance when we are looking at the file metrics. So, what this actually does is it takes a structure. So, it takes a structure of a language such as English or um, French, maybe even some of the Eastern languages, and then it assigns a mathematical set. So of course it sets a mathematical set of rules, and then we can actually define these sets of rules, and uh, we can build a language. Language in the sense of mathematical sense, or one which is useful for S25. Okay, so if we look at the languages around the world, we see two types of languages in terms of uh, down. Okay. So we have two types: subject object verb and subject verb object. So here it's like English, French. Here we have things like some sort of Eastern languages, like from where I'm from, we have Hindi. We also have Kannada, Telugu, and many other such Indian languages, along with maybe even Mandarin and uh, things like that. So now, what is the lowest language that is possible uh, using this mathematical definition? Uh, Not exactly the lowest, but somewhat reasonable. Uh, I'll say these sets of rules. So every word is 2 digit long, and then every subject and object follow this particular thing. So the first, so first let me just look at what I have done. Okay, so first digit is always odd, and second is even. For action, um, first is even, second is odd, and rest are redundant. So now you can ask me what bearing, or what in what way is this actually a language? So um, again, so if I can explain this in many different ways. One way I can do is I can look at natural language processing, or I can just start off with a mathematical kind of equivalence thing. So let's do that. Uh, so I'm going to say every language has these kind of three parts to it. I mean, like the very basic sentences. So we have the object part, or this is the physical part, and then we have action. So these refer to some action being performed by something, and then we have the connector or the helper. So we take one object with using the helper word, we associate it to some action. So that is what the actual language looks like. Yes, and this can be represented in terms of a set, and then we have these kind of connections between these sets, which can form sentences. Uh, so again, we can actually expand this in terms of adjectives, adverbs, and other things. Uh, Again, these objects can be divided into many sub objects, like when talking about oneself, or maybe talking about someone who's very close to you, maybe versus someone like an acquaintance. And of course, there are like many such things, and uh, we can kind of divide everything into this format. Before we move further, we can just look at natural language processing. So natural language processing is a part of recurrent neural networks, also called as RNN. So basically what we have is we have one layer, and then we have hidden layers, and then we have an output layer. And of course they are connected by some means. And of course this can come back, and that is the reason it's called recurrent neural network. So what generative AI right now does is it uses something called as a bag of words trick, or some kind of yeah. So first they use a bag of words trick. So you have certain bags, and then if you have a sentence, let's say every word is two digit long, so it just stores every word in its bag. So this is sentence one, uh, and this is going to be sentence two, and then it kind of stores all of these words, and then when we kind of try to classify it based on a particular metric, it actually looks at what words there are, and then it kind of captures it. And the other one uses something called as a Markov process, which is called as long short-term memory. So when we have a very long set of words, let's say I have x1, x2, x3, x4. If I want to generate xn, it looks at xn minus 1 and so on. This is the long aspect, but it gives more importance to the short term kind of a message. So again, I'm not a computer science expert, but these kinds of things are what AI do to actually generate these responses. And of course, this has to be trained from with a huge amount of data. So if I were to define a language, then I have to define a huge amount of data. And yeah. Okay, so coming back to our example, uh, we have first digit is odd, second digit even, we get a subject or an object or a person. If I have first even and second odd, then it's an action. So now assuming, so now let's look at a sentence in this, in the SVO kind of language. So again, so it's going to be like 1 2 2 1 1 2. This is a valid sentence because 1 2 subject, 2 1 verb, 1 2 is the object or subject. We can be interchanged. That is not an issue. Um, yeah, so this is how the language redefinition module works. I mean, in terms of defining a language. Of course, if I have a much more complicated language, then I may have to use more, either more number of digits, or maybe even more kind of like this rule book. Okay, so right after this, we have to define what exactly collision means in this case. So now that we have the actual definition, let us look at collision. So what we classify as a collision in when working with S25 is that when the attacker, so let's say the actual receives 122112 and the attacker receives 142112, 122112, 324112, and many such valid, it should be valid. So anytime we have a hit with so let's say the attacker applies some strategy and he finds some of the valid sentences. So for every valid sentence, we are going to assume that there's a collision. So if we do get something like 242112, we know that this is nonsense because this is a redundant word. So this is not a collision. So of course, this is the basic part. So what I can also do to this language redefiner module is that I can add redundancies. So what happens with redundancies? Consider a statement like this: 12222114 41253. So this is the particular example that I will be talking about. So again, this is not collision right now. Okay, so with a sentence like this, it's a little bit confusing on what exactly is going on. So let us break it down. So let me just write down the rules again. Odd even is subject, even odd, action, rest, redundant. Okay, so let's look at what exactly is going on. 1 2 refers to a subject. So if I want to look at the original kind of a sentence, what I have to do is I have to write down all of the non-redundant words. So I'll be writing 1 2. Next 2 2. We know that it's redundant because it doesn't fall under those two, so I'll just ignore it. 2 1 is an action, and then 4 4 is redundant. 1 2 is again an object, and 5 3 is redundant because both of them are odd. So this kind of a redundant mess reduces into a valid function, and that is how we check for redundancies. And then how we reduce, so how we check for if redundant sentence is valid or not. So of course there can be many such rules. So in this case I've taken every word should be followed by a redundant word, or one can add a redundant word right in the middle or just before an object. There can be many such combinations of what we actually do. So now let us look at what a collision is here. So I can have 1 2 4 4 2 1 4 4 1 2 5 3. Let me just write it down neatly. 4 2 2 1 4 4 1 2 5 3. As we see that the redundant bit is kind of messed around. So this is considered as a collision hit. So if we have two bits which have changed, if it is 1 1, there is still a collision hit when it's redundant. So redundancies can be a powerful tool to add to the sentence to actually make it much longer, artificially, of course. In this case, these four are going to be considered as a word. I mean, if you do want to consider it, but when I keep it as a redundant option, I can get much more flexibilities. For example, I can use it to increase it very slowly. So I can take 1 2 2 1 4 4 1 2. So this is the only redundant bit, and the rule corresponding to this is that uh, uh, every action is going to be followed by a redundant bit. So, or on the next stage, I can put every subject is going to be followed by a redundant bit. And of course, this increases the security as well as um, it gives me a direct file size control. Okay, even though the reduction is going to be the same, this is still considered as a collision because this refers to two different instances in the actual file. So when it comes to S25, these redundancies play a huge role in terms of one adding length to the sentence and also controlling the file size along with some of the increasing security measures. Okay, now all we have to do is we have to define a distance metric. Um, so let's look at distance. So if I have K1 and K2, the distance is just going to be Manhattan distance, but whenever we have this mod 10, there is going to be this kind of plus or minus kind of thing. So we take, so let's say K1 is equal to 9, 5, and K2 is going to be equal to 1, 4. So when we look at the actual difference, what we are going to get is either like 1 minus 9 or sorry, 9 minus 1 and 5 minus 4. So this is going to be something like 8 1. So 8, again, when we are looking at absolute distance, we take every digit or every word individually. So this is going to form 1 and this is going to form the other. So it is going to be, and then everything is added up. So we have 9 minus 1, which is going to be 8, and 5 minus 4, which is going to be 1. But there's a issue here. So if I were to take 9 and if I were to add 1 to it, I'm going to get 0 mod 10. So and the difference between 0 and 1 is going to be 1. So this is going to be 8. Sorry, this is going to be 2. So now how do we actually define the distance? I define it as the minimum of the difference mod 10. So if I have, let's say K1 consists of um, N0, N1, dot dot dot, and then K2 consists of M1, M0, M1, dot dot dot. Distance between K1 and K2 is going to be absolute, and then there's a minimum, Ni minus Mi. And then of course this is going to be under summation. So this is how I'm going to define my distance. Again, why I'm defining this distance is going to be, yeah. So why I'm defining distance is going to be much more kind of integrated into S25. So let us look at an encryption scheme as of now. So we are arriving at the second part of the encryption decryption process. Uh, so what I'm going to do right now, so let's say I have a message M. So again, to keep track, I'm going to write which of them are LRM valid and which of them are not. So message M is LRM valid. Sorry, LRM invalid. LRM invalid, right? sorry, M is LRM valid. And then I have key K1, sorry, KI. So KI is invalid. Okay, so now we are going to look at an encryption module which is called as E between M and KI. Sorry, M and KM. So E of, sorry, please forgive me. M is the iteration. So if I have the first message, then I'm going to call M is equal to 0 or M is equal to 1. Okay, I'll call it M is equal to 1. And of course, all of them are invalid. What we are going to do with this encryption module is going to take it to the closest LRM, which is possible. And let us call the distance between Km and some LRM D. Okay, so let us just go over this once again. M is the number of iterations which are already done or is going to be done. Km is the key which which I need to send to the other person, and I'm going to be encrypting this in LRM or in language redefinition module or something which has a rule set. Okay, so now what I'm going to do is what I'm just going to take T plus or minus. So again, we are following the plus or minus rule from. Okay, let me just explain that part again. So if I have a message which is LRM invalid, so let's say I have. Okay, so let's say I have N1, N2, N3, and so on, which is LRM invalid. If I want to make them LRM valid, what I can do is I can change I can add or subtract one from the particular digit which are not following the LRM. So now if I have N1 equal to 2 and N2 equal to 1, we know that both of them contribute to the invalidness of LRM in the first, which is defined before. So this has to be either 3 or 1, and this has to be either 0 or 2. So this is the transformation that we are applying to the invalid message to get a valid one. And if it does follow the valid nature, such as n3 equal to 2, then we don't do anything. So let us call this process t plus or minus. So uh, so t plus or minus km. So this takes km to all such kind of uh, variations, and of course what we are looking for is the minimum distance to encode actually. So this is going to be equal to t plus or minus km such that the distance between km and t plus or minus km is equal to minimum of dkm give t plus or minus km. So let's unpack this little by little. I have m as the number of iteration. My key is km. Km is referred to is going to be this invalid LRM country. It can be valid in the case the distance is going to be 0, and e of m km is going to be km. Uh, so this transformation, what it does is it looks at every single alarm uh, valid or whatever it is. So it is going to be some arbitrary transformation, and of course it's going to either add or subtract some number. So we are trying to minimize the distance or the Manhattan distance between T of km and then km. So that is going to be my encryption. So what this looks like on a graph. So let's say that this is my km, and I have all of these sets of, let's just denote it by process. So what t does is t plus or minus, it takes it transforms this into all of these LRMs. So cross is. So what this function does is it takes one of these km's and then it calculates the distance between all of them and then chooses the minimum distance LRM, and that is going to be my encryption scheme. Of course, so when we are looking at S25, E of 1 comma k1 is actually equal to k1. There is no LRM being applied on the very first key. I hope this makes sense, and I think I've clearly referred to everything. If there is some ambiguity, this will be again explained in the practical demo, because this is the exact same thing which I'm using. Okay. So now we need to prove okay, before I go further, another aspect of LRM is AI. So what is the exact role of AI in LRM? LRM can be static. Of course, so when we have something like a static LRM, over time, as the capabilities of machines changes, we have to keep redefining LRM, and every time we redefine LRM, we have to train the AI. So, for example, if an AI has to be trained in English and say in French, it has to be trained on two separate um, very high powered machines. But what happens if I add in AI into the LRM is that I can evolve LRM as the machine capacity evolves. That means that my AI is now, this LRM along with the AI is now much more friendlier to train. Uh, and that is where the AI is going to come in. So when we look at human language, when we look at history, we have dropped O's. So from COLOUR, we have dropped the U, and and in many other cases we have abbreviated. So at the moment became ATM, and of course we do have many such abbreviations like TTYL, GTG, or FR for real. TTYL, GTG stands for talk to later, got to go. And then we have these kind of things which are evolved because we are introduced to texts. So one of the theories that I have is that because we moved from a noisy channel, which means air, to somewhat of a very noiseless channel, which is texting, we don't need to represent everything in terms of uh, you know a very long redundant message. We can actually get away with things like using ATM and other such abbreviations. Of course, now there are many more, and it's going to keep evolving. So if we can set the AI to actually mimic how the human language evolves, we can actually expand and reduce the size of LRM. and particularly we can change about the settings of the number of bits used versus the entropy, and that is going to be the one of the arguments that is in the size method. So we have 2 to the power alpha minus epsilon, times summation of ki. So this metric is going to be directly under control when I'm changing both epsilon and alpha. So alpha is the number of bits and epsilon is the um, entropy of the language. So of course, if we look at human language evolution, this is actually going to decrease. But if we look at the from the other time reversal kind of thing, this actually starts to increase. Uh, so we have ATM becoming at the moment it starts to expand, and this presents a new scale to the protocol. Of course, again, the traditional way to scale is of course using KI and some static LRM. So keep increasing the messages, but after some point, this is going to start to become very large. So what we can do is that we can control this and this to maintain a very good hold of the size metric. So that is where the AI comes in. And of course, when we do evolve it, we can use a quantum AI, which does all of the same thing the AI does. Uh, I mean, like this part is one module kind of thing. Because this is going to be dynamic. We can use a quantum AI, and the way I envision it is going to do the exact same thing as language checker. So if I were to have a sentence and send it to one of the LLMs present right now, sorry, the generative AIs that are present right now, it has the capability to see whether it's a correct sentence or a coherent sentence or not. So what quantum AI does is it takes a message and then it checks for all of these kind of closest language redefinition module things, and then it kind of stores it in the registers in different rotations. So essentially, it acts like a quantum database. Sorry, it acts like a database where you can keep checking it, but it uses quantum mechanics. Again, it's not too fancy. This is not required at the moment. We are going to be using static. If S25 is implemented, we are going to be using static LRMs for quite some time. At least, I don't know, maybe another 20, 30 years. Okay, so now we move on to the cascade function. So first thing we need to prove is that this actually drops down to a unique state. Uh, so now proving, proving this was quite a challenge for me. Um, of course, I cannot use any traditional methods, and maybe I'm not smart enough to use traditional methods. So what I did do is I looked at the case where the cascade fails. So now let us look at, so if the cascade fails, so let's see, if I have the file, so I'm going to represent the states as positions. P, uh, K. K is the number of items. Sorry, I'll just put this as M because we used M in the previous thing. So PM is the state. Of course, there's going to be a key here. So PM of K is going to be uh, the position of kth instance after m iterations. So P1, P2, P3, these are all the number of uh, iterations, and then k represents the position of the kth iteration. So now let us look at when failure actually happens. So the sentences, this converges always to a unique state. So now I'm going to look at the failure case. So failure is Pm of k equal to Pn of k for all k's. Okay. Um, what this says is, sorry, I'm not good. So for different values of m and n, I'm getting the same state. So that is the failure case of the cascade function. So now, because I cannot prove it for, let's say, some arbitrary thing, what I can do is I'm going to assume that the first state exists. So first state, I'm going to look at two specific values, P1, sorry, Pm of 1 and then Pm of max. So now let's say I have some messages. Again, after every such iteration, it moves forward. So Pm of 1 is actually going to be after, let's say, m minus n. So after m minus n iterations, so I'm going to get from Pm to Pn. So Pn of 1. And then I'm going to have a Pn of max. So now there are two cases. So one is after n iterations, the max function actually doesn't reach the end of the file, and it reaches the end of the file. So once it reaches the end of the file, there's a possibility that Pm max can actually be Pm max. Sorry, let me just write it down. So which means that before Pm max there should be one more Pm max minus 1. So Pm max minus 1 moves to Pm of max. So after n iterations, Pm of max is going to be equal to Pn of max. That is the case if the file ends. If the file does not end, we already have a contradiction which says that I have this n kind of Pn max is not equal to Pm max because the file has the position has actually moved after these many iterations, which actually contradicts the final in the case of failure. So in this kind of a case, we look at Pm of 1. So if Pm1 of 1 cannot be equal to Pn of 1 in any case, because once the file moves, it cannot actually stay there. So if I have one instance like this, after the message has moved, again it has moved, again it has moved. So after 3 iterations, if it is the same, it is not possible at all. Unless we are looking at a cyclic file, but we are not considering a cyclic file. So Pm of 1 can never be equal to Pn of 1. So that means that the failure case is not actually present. So briefly, let us look at when we encounter such a thing. We'll take the simplest case and look at what the file looks like when we have a failure. And of course, this can happen, but it's extremely rare. But we do have to cover it. So let's say I have K1, K2. This is my original file. So I have some Kn, and then I have Kn plus 1 and something. Then Km plus 1, and then end of file. If Kn and Km, these kind of series, are both equal and I somehow manage to land in these two positions, only then I'm going to get this kind of an error. where the cascade function does not completely reduce down. But these are randomly generated bits, and the probability of something like this happening is extremely small, especially in the very large cases. So we are usually going to get a unique state, and of course, if we do run some simulations, we can actually show that these kind of things occur at most two times. I mean, like we may reach kn is equal to km, and then maybe kn plus 1 is equal to km plus 1 kind of thing. So the conclusion is, if the cascade function cannot not I mean, like, it has to reduce into a final unique state under the conditions that I put on S25. Uh, Other than that, I do not actually see any such possibilities. And of course, this is a proof by contradiction. So I'm assuming that the cascade function has Pm of k equal to Pn of k, and then after certain iterations, they are not equal. I mean, like, they're equal, but then if I look at the very first and the very last message instance, I'm going to be saying that because of the construction of S25, it is not possible for them to be equal. So that is how I prove the existence of a unique state after the cascading function. Okay, so there's one more final part that I have to mention, and it is the equidistant problem. And what happens when the decryption fails? So let us take this particular case. So let me say that I have 1 2 2 1 1 2. This is the only valid LRM. Of course, this makes it easier for me to demonstrate what exactly I'm saying. So let's say that my initial Ki is going to be 142112, and this is the message that I have chosen. Now this, when I apply the nearest valid alarm, I'm going to be getting this one. So what A does is, A sends this message. But let us look at it from the B perspective. So B receives this message, and using the reverse encryption scheme, what he does is he looks at this particular thing. He has both of these states, and then he looks at both of them and says, "This is the closest I can find." So I'm going to ignore this. But A has chosen what he has ignored. So this, I'll call it the equidistant problem. So now I have some solutions for this. Of course, there are three solutions. And let's look at a general case. So if LRM of I and LRM of J are closest to each other, which means that no other LRM are, have the same. So if I take LRM I, LRM J is the closest LRM, or one of the instances of closest LRM. So now, if I were to take both of them and plot them, so let's say one of them is here and the other is here. So I is here and J is here. So now let us look at all of the digits in between them, all of the non-valid ones. So if I have two of them, if I were to choose here, I have to go to I. I do not have the option to go to J. If I go to I, then I know that this is the thing which is closest. If I were to send J, I know that this is the closest. So let's call this message 1 and message 2. So if B receives, I, then B knows 1 is the closest. Otherwise, B knows that 2 is the closest. So now what happens if I introduce a third point? So if I send in I have the ambiguity whether it's either 1 or 3, or if I use J, then it's either 2 or 3. So in instances where, so the statement, so instances between closest LRM, if it contains 3 or more invalid messages, we are going to encounter a decryption failure. So, of course, there is always a chance that it can pass, but there is a chance that it can fail. And of course, the more number of points we have, the more chance of failing occurs. So now, how do we actually solve such a case? One naive way of thinking is to make sure that LRM doesn't actually have that condition. And of course, if this exists, then I cannot define, I cannot have the freedom to define LRM however I feel like, especially when it comes to alpha minus epsilon. So alpha minus epsilon is the restriction, and I cannot freely manipulate. Another way is to include distance bit. So when I include distance bits, not only am I increasing the security, I'm also I'm also reducing the receiver space while maintaining the amplification in the attacker space. So this is one of the way, and the other way is to invert the problem. So when I invert the problem, I'm looking at what Ki have the closest LRM to the given LRM. So B has K1, K2, and so on. Which of these have the closest LRM to the incoming message, or let's say this message is MK. So which of these are the closest to MK? And that is actually going to increase the complexity of uh, the decryption process, but it actually provides some amount of security. So if I include the distance bit, what ends up happening is the error of MMI minus 1 can be either in the message or the distance bit. When this sort of thing happens, the attacker space blows up, because if it's in the distance bit, they cannot actually look at the distance. If it's in the message bit, they cannot look at the message and kind of take the distance. And because the receiver space reduces very quickly under this kind of a thing, the attacker has much less chances of getting the actual message or the actual state. When we invert the problem, this actually provides a good control on the state reduction, or it offers a slower reduction state. So if I have a huge space, and if I want to maintain that huge space for the next iteration, then I have to invert the problem, and then I'm going to remove all of the cases where it just doesn't work. So yeah, so that is all the theory behind S25. So next we'll go into the security metric.